All right, so I'm going to go over the first half of our electrostatics review. Let me pull up my screen share here. All right, so I'm going to look at maybe just the first 4 questions. And so let's take a look at number 1. So number 1 says, the diagram above shows an isolated positive charge Q. Point B is twice as far away from Q as point A. The ratio of the electric field strength at point A to electric field strength at point B is. All right, so if I come over to my whiteboard right here, basically wants to know what happens if you're twice as far away from a charge. What happens to the electric field strength? So I'll write EA to represent the electric field strength when it's a distance R away. And then EB will represent the electric field strength when it's a distance 2R away. And so our equation for electric field is KQ over R squared. And therefore here it would be KQ over 2R squared. 2R squared because that's twice the distance now. And so if we take the ratio of these two, and we want to know how much stronger it is, well, then we would just do EA over EB. We can see that these KQs will cancel, and what we're left with is 2R squared over R squared, which is equal to 4. And so our ratio then, I pull the test back up here. Our ratio then is going to be a ratio of 4 to 1. It's 4 times as much if you're twice as far away. Okay, so number 2 says, it says we have a diagram on the right shows the electric field lines in an isolated region of space containing 2 small charged spheres, Y and Z. Which of the following statements is true? If you look at this diagram right here, you can see that the electric field lines go out from Y and they go towards Z. And so what that means is positive charges have electric field lines that go out from them. Negative charges have electric field lines that go towards them. And so right off the bat, I can say A isn't true because Y is a positive charge. It has those field lines coming out from it. The strength of the electric field is the same everywhere. And well, no, it's not, because I mean, just look at our last problem. It involves the radius squared, so it definitely depends on distance. The electric field strength is strongest midway between Y and Z. Well, although the electric field does add up, although they add together there, the electric field gets stronger as you get closer to the source. And so therefore, if you get really close to, say, Y or really close to Z, the electric field is going to go up, and that's proportional to the distance squared. So the smaller that distance is, and because it's squared, the field strength is going to increase exponentially as you get closer. And so it's not necessarily, well, it wouldn't be midway between Y and Z. D says a small negatively charged object placed at point X would tend to move towards the right. Well, that is true. If you take a look at the electric field lines, they point towards Z. But remember, think of the electric field lines as pointing in the direction where a positive charge would go if you placed it there. But if you place a negative charge there, it's going to be going in the opposite direction. So it's going to be going towards the right. So D is true. So for this question, the answer is D. All right, number 4 says we have a negatively charged rod brought near but does not touch the initially uncharged electroscope, and the leaves spring apart. That's picture 1. And then the electroscope is then touched with a finger, the leaves collapse. That's picture 2. And then when the next finger and finally the rod are removed, the leaves spring apart a second time. That's picture 3. And it wants to know what's happening to the charge on these leaves. Well, if we bring a negatively charged rod close to a neutral conductor like this, what's going to happen is these negative charges in this rod are going to repel the negative charges in this conductor. And so the effect of that is the negative charges are going to be pushed really far away. They're going to be pushed into these leaves. And the positive charges are going to be brought close to this rod. And so the leaves are going to be negatively charged because of this charge repulsion that's happening here. And so in the first picture, the leaves are negatively charged. And then if you bring in your finger right here, your finger's sort of acting as a grounding wire almost. It's essentially giving a place for those negative charges to go now, an easier place for them to go. And so if you touch your finger to the rod and to the electroscope, those negative charges are now going to be going into your hand. And so your hand will become negatively charged a little bit. but the effect of it is to sort of balance out all the charges. The effect will be to balance out all the charges here, so there's no net charge between these three things, because the negative charge has gone into your hand and probably distribute itself throughout your body, or if it can, it would go in towards the ground. So right in picture 2, it's neutral. Everything is neutral. Well, what happens if you then bring your hand away? Well, those negative charges now have gone into your hand, leaving an excess positive charge on the electroscope. And so the electroscope then would have a positive charge and would repel each other. So the leaves would repel each other. So in picture 3, there's a positive charge. And so the answer would be negative. So it'd be D. It would be negative in 1, positive in 3. All right, I'll just do, let's see, how much time do we have? Okay, I'll go ahead and do just number 5, and then we'll do 6, 7, and 8 next video. Number 5 says a positively charged conductor attracts a second object. Which of the following statements could be true about it? Well, if you have a positively charged conductor and it's attracting something else, well, let's just take a look at the options and see. So the first option says the second object is a conductor with negative net charge. Well, yes, that could be true. If you bring 2 conductors, say 2 metal spheres close to each other, and one has a positive charge, one has a negative charge, they will attract each other. And so 1 could be true. 2 says you bring in a second object, second conductor, so another, say, metal sphere, and this time it has 0 net charge. Could it still be attracted to the positively charged one? Well, let me bring up my board right here, because if something is attracted to something else, that means there's a net force acting on it. And so if that's the case, then you could say, okay, F is equal to K Q1 Q2 over R squared. If one of the charges is 0, doesn't that mean that there's doesn't that mean there's no net force? Well, the answer is no, because think about what happens. Let me bring back up my screen share. Think about what happens. Well, think about what happens when we brought that negative rod towards that neutral object. And so when you bring it towards a neutral object, it's going to push those like charges. So if you have a positively charged conductor and a neutral conductor, bringing them close together would have the effect of pushing those positive charges away. It's still going to be on that surface. So the net charge is still going to be 0, but it's going to push the positive charges to the other side of the sphere, and it's going to attract all the negative charges to the side that's closest to the positively charged conductor. And so it will have an effect of creating an attraction, although it's important to note that when you charge something by induction, which is sort of what would be happening here, you need a place for that excess charge to go. So when we were using the electroscope and our fingers here, we had a place for that excess charge to go. It was into our hand. So if you were to do this experiment, bringing a negatively, if you were to do this and you only had 2 objects but nowhere for that excess charge to go, it will attract it for a moment. But then when you bring those 2 things apart, when you bring those 2 conductors apart, the one that was neutral will remain neutral, and eventually the charge will distribute itself evenly again. So you need somewhere for it to go. And so 3 is not, couldn't be true, because insulators, well, the difference between a conductor and an insulator is a conductor, typically metals, are objects where the electrons aren't tightly bound to their nucleus in the atoms. And so they can kind of flow freely through a conductor. Whereas an insulator, those electrons are tightly bound to their nucleus, and therefore they can't move easily. And so 3 couldn't be true, because you can't charge an insulator, at least not easily. You can't. For most purposes, you can't. And so the answer would be 1 and 2. It would be D, 1 and 2. All right, so for the next video, I'll finish the exam.